Welcome back to Physics 191. I'm Gerard Blanchard. We left off last time with an example of a basketball player jumping up in the air to slam dunk a basketball, and we found out that even though we didn't know his mass, we could calculate his acceleration while he was in the air. If you remember, his acceleration was negative g, or his acceleration in the y direction was negative g, and the reason that came out to be is that we used Newton's second law, and the only force acting on him was weight or gravity, which depends directly on his mass, so that when we divide that force by his mass, the masses cancel out and we're left with the acceleration being equal to g in the downward direction, or in the negative y direction. It didn't matter whether it was a person, as it turns out. It could have been any object. Anything that has mass will still have this situation. So this actually makes a special situation in kinematics, a special case of kinematics, and we're going to call that free fall. Free fall is a term that we use to refer to the situation in which the only force acting on an object is its weight, or gravity. Now, for us to be in a free fall situation, the air resistance must be negligible. We must be in a case where we don't have to consider air resistance. Now, despite the term free fall, the object doesn't need to be falling. It could also be rising, just as we found when Grant Hill jumped up in the air. And when we're in the situation that the only force, or the total force, on an object is equal to its weight, well, we'll put that into Newton's second law to calculate that the acceleration vector is equal to the weight vector divided by the mass. And remember that the weight is mass times g, so the mass in the numerator and denominator cancel out, and we're left with that the acceleration is 9.8 meters per second squared in the downward direction. So it doesn't matter what kind of object it is. As long as it's in the air and the only force acting on it is gravity, the object's acceleration is going to be 9.8 meters per second squared downward. Now it tells us a couple things. It tells us that it's accelerating in the negative y direction if we draw our y-axis up. It also tells us that the acceleration in the x direction is 0. So this brings us to another type of situation, and we're going to call these projectile situations, meaning that something is projected or thrown. It can be thrown up in the air, it can be thrown up into the side. As long as it's up in the air, we're dealing with a projectile situation. Now, a projectile situation is a kinematic situation. And how do we identify a projectile situation? Any situation in which an object is in free fall, which means, once again, that the only force acting on it is gravity, then, for our general equations, we have our kinematic equations, plus we have a little bit extra knowledge. We know that the acceleration in the x direction is 0 meters per second squared, and the acceleration in the y direction is negative 9.80 meters per second squared. Let's see what kind of motion we get out of that. Let's assume that our object starts from the origin, so that would be x initial equals 0 meters, y initial equals 0 meters. And we take our special knowledge. Acceleration in the x direction is 0 meters per second squared. Acceleration in the y direction is negative 9.8 meters per second squared. Let's start with our x kinematic equation, specifically x final minus x initial equals vx initial times change in time, plus ax times the change in time squared. And putting in x initial is 0 and acceleration in the x direction is 0. That simplifies to x final equals Vx initial times the change in time, and we can solve that for the change in time equals x final divided by Vx initial. Let's use the same equation in y. Y final minus y initial equals Vy initial times the change in time plus Ay times the change in time squared. And into our y equation, we're going to put in that y initial is 0. We're going to put in that the change in time is x final divided by x initial, and also that the acceleration in the y direction is minus 9.8 meters per second squared. And this gives us an equation for the y position of the projectile of y final equals Vy initial times x final over Vx initial minus 9.8 meters per second squared times x final divided by Vx initial, and that quantity squared. And that gives us the final equation that I was trying to get to of y final equals Vy initial divided by Vx initial times x final minus 9.8 meters per second squared divided by Vx initial squared times x final squared. So we see that our final y position at any time depends on our x final and x final squared, or in other words, the path that the projectile follows is a parabola. Y is a function of x and x squared. That means that the projectile follows a parabola. And also, since the parameter in front of the x final squared is negative, it's a downward curving parabola. Now, the exact parabola that we have depends on our initial situation. You'll see that the initial slope of the parabola depends on the initial velocity in the y and the initial velocity in the x direction. The curve depends on, or the curving, the downward curving, depends on the initial x velocity. So all thrown objects follow a parabola, but the exact parabola that they follow depends on the initial conditions. Let me just show two examples of this. What I'm going to do is I'm going to graph y versus x. In this first example, I'm going to make Vy initial equal to 0. So we're dealing with an object that's thrown straight out, not up, not down. So imagine that you're standing on the top of a building and you throw a ball straight out from the building. You don't throw it up and you don't throw it down, you throw it straight out. Well, it's going to initially move straight in the x direction, but over time it's going to curve down. And that is an example of this graph right here, where we have a parabola that starts from 0 and 0. We assume that the initial position is 0. It starts off moving completely in the x direction, but also immediately curves downward. So the ball that you threw off the roof of the building will follow a downward curving parabola that it was initially moving straight in the x direction. So that's one example. In another example, let's assume that you're standing on the ground and you throw a ball and you throw it both up and to the right. Well, that would be something like this graph right here, where we have a parabola that starts from x is equal to 0 and y is equal to 0. And it's initially moving upwards and to the right because that's how you threw it. But over time, the ball will curve downwards and it will once again follow a path of a parabola. So all thrown objects move in a parabola as long as we can ignore air resistance. The parabola, the exact parabola that they follow, of course, depends on the initial conditions. The angle at which you threw it, and also the speed with which you threw it. Now let's take a look at some parabolas that might be easier for you to visualize. What I'll be doing now is I'll be doing a demonstration of projectile motion to show you that a projected object, a thrown object, follows a parabolic path. And the way that I'll be demonstrating that is I'll be using a water hose. Now, the water that comes out of the water hose is not exactly in free fall, so we won't get a perfect parabola. There are other forces on each water molecule. There are forces between the different water molecules. They're pulling on each other. And there's air resistance. So we have to ignore those to get a perfect parabola. But those forces are small enough that we will get a very good parabola, just like I will be drawing on all of my diagrams. So let me just turn the water on. And you can see, let me steady out. You can see how the water follows an arc. That is a pretty good parabola. And that'll be the trajectory of any thrown object. And what I'll do is I'll use this ruler and to give you an idea of the initial velocity of the water. The hose is following along the path of the ruler down here, and so when the water leaves the hose, it's initially moving in the direction of the ruler. So that would be the angle of the initial velocity of the water. What you can see is that the water is initially going in the direction of the ruler, but as soon as it leaves the hose, it curves down. It curves away from the ruler. Now that's true no matter how I angle the hose. If I were to hold it straight out, then the water is initially going horizontally as it exits the hose, but as soon as it leaves the hose, it starts to curve down, and you can see it's making about half of a parabola right now. The same thing you can see if I'm initially projecting the water downwards. If the water has a downward initial velocity, at the moment it leaves the hose, it's moving in the direction of the ruler, but it immediately curves down. So I can get a whole bunch of different parabolas. I can make it initially curve up, initially go to the side, initially go down. In every case, the path of the water is part of a parabola. Now let me show you a few other things. First, if I were to move the hose very close to the ground and point it along the ground with zero angle, you can see that it doesn't go very far. Okay? As I change the angle of the hose, two things happen. One is that the height, the maximum height that the water reaches, gets higher. So the more y velocity the water has, the higher it goes. Also, it starts to move a little further out. Now, if I continue to angle the hose, the more I angle the hose, the more initial y velocity the water has, and the higher and higher it reaches. And also, it also has more range. It moves further out. Now, as I keep angling it up, there's some maximum range. As you can see, the water's still going higher, but it's not moving out any further. So that would be the maximum range of the water with this initial velocity. If I angle the hose higher, then the water continues to go higher, but it doesn't go quite as far. And if I come back far enough, it'll go right back on top of me. So that is the farthest, at that angle, that's the farthest that I can make this water go. The only way that I can make it go farther is to increase the initial velocity. I'll do that now. So by increasing the initial velocity, let's see, there we go, I can actually get the water to go out further. So there's two things that we can change. We can change the angle of the initial velocity, and we can change the initial velocity, the speed of the initial velocity, the magnitude of the initial velocity. Now here's one more interesting thing. If I initially project the water out horizontally, this is 1 meter. So when I project the water out horizontally, I know exactly how much time it'll take that water to fall 1 meter. To fall 1 meter, it's a little bit less than half of a second. That would be our y equals 1/2 gt squared, or y minus y0 is 1/2 gt squared. So I know that for the water to fall 1 meter, it takes a little bit less than half of a second. Now, since I know that, and since I know that the water travels at constant velocity in the x direction, I can figure out the initial velocity of the water. Let me change the initial velocity until it moves about 1 meter in that direction. That's close to 1 meter. So now, since I know that the water falls in half of a second, and in that time it moves 1 meter to the right, I know that it is moving in the x direction, it's moving 1 meter in half of a second, or its initial velocity is 2 meters per second. I can make the water go farther by increasing the initial velocity. Now I would say that the water is going about 5 meters in that 1 second. Well, not quite 5 meters. That's maybe, we'll call that 3 meters. The water is going 3 meters in the 1/2 second that it takes to fall. So now I know that the initial velocity of the water is about 6 meters per second. So when you throw something horizontally, you can figure out the initial velocity just by measuring the distance that it travels while it falls. So let's take one more look at these nice parabolic arcs. So whenever you have an object in free fall, remember to draw its path as a parabola. So remember, whenever you're drawing your diagram for a free fall situation, to draw the object moving in a parabola, just like we saw the water from that water hose moving. That's all. Whenever you throw an object, whenever an object is dropped, it follows those graceful parabolic curves that we saw with the hose. Now let's do an example. A ball player standing at home plate hits a baseball that is caught by another player at the same height above the ground from which it was hit. The ball is hit with an initial velocity of 22 meters per second at an angle of 60 degrees above the horizontal. How high will the ball rise? How much time will elapse from the time the ball leaves the bat until it reaches the fielder? At what distance from home plate will the fielder be when he catches the ball? Now, this is the way that physics situations are often presented, but what we have to remember here, what we have to realize here, is that we're actually dealing with two different situations. We're dealing with two different time frames. And what are they? In both of the time frames, the ball starts from home plate and it's going up at 22 meters per second, an angle of 60 degrees above the horizontal. But there's two different endpoints. The first part of the question asked, how high will the ball rise? So our time frame there, or our end time, is going to be when the ball is at its highest point. So that's actually one situation. The other half of the question, how much time will elapse from the time the ball leaves the bat until it reaches the fielder? And at what distance from home plate will the fielder be when he catches the ball is actually a second situation, a second time frame. So we have to break this up into two different situations. The first, with the ball going from home plate to its highest point, where it's neither rising nor falling, but moving only in the x direction. So, draw a diagram of that first situation and see if you can answer the question, how high will the ball rise? How high will the ball be when it reaches the top of its parabola? Remember to draw the ball moving in a parabola. Okay, let's draw our diagram. We have to draw both our x and y axes now. Since the ball is moving in two dimensions, we'll start with the ball at the origin, and it moves up in a parabola. And for the first half of the question, the ball stops at the top. So here we have t initial, which is going to be 0 seconds. And we have x initial, which is 0 meters. Y initial is 0 meters. Vx initial. Vy initial. We'll have to think about that. And then we have t final, x final, y final, vx final, vy final. You have to consider the acceleration of the ball, ax and ay. Well, ax and ay, we know that since the ball is in the air, we have a projectile situation. So we know that ax is 0 and ay is minus 9.80. Let's see. We're told that the ball is hit with an initial velocity of 22 meters per second at an angle of 60 degrees. And I do believe that that's all the information that we're explicitly given. There is one thing that we can infer from the fact that the ball is at the top of its arc, and that is when it's at the top of its arc, it's neither moving up nor down. So we know in this case that Vy final is equal to 0 meters per second. It's not moving in the positive y direction, it's not moving in the negative y direction. All the rest we don't know. Let's think about Vx initial and Vy initial. How is the ball moving initially? Initially, it's moving both in x and in y, so that it's moving to the right and it's moving up. So what do we have to do? We have to break our initial velocity into an x part and a y part. And I'm going to draw that over here bigger so we can see it bigger. 22 meters per second. And Vx initial, Vy initial. So what I've done is I've taken this and I've drawn it bigger. Taken this little triangle right here, drawn it bigger, and we know that x and y are perpendicular to each other, and we know that this is a 60-degree angle. So now we see how to break up our initial velocity into x and y initial velocities. Vx initial is adjacent to the 60-degree angle, so it's going to be our adjacent side. So we know that Vx initial is going to be 22 meters per second, cosine of 60 degrees, and y, Vy is opposite our 60-degree angle, so we know Vy is going to be 22 sine of 60 degrees. And we can calculate those. 22 times cosine of 60 degrees gives us 11 meters per second, and 22 times the sine of 60 degrees gives us 19.1 meters per second, and that's actually 11.0. So Vx initial is 11.0 meters per second, and Vy initial is 19.1 meters per second. So we have now completely analyzed the question statement for the first half of the question. We have to now identify the type of situation that we're dealing with. We're dealing with a kinematic situation. What do we want to know? Let's remind ourselves, what do we want to know? We want to know y final, the final height of the ball. Now, as far as y is concerned, we know Vy final, we know Ay. As far as y is concerned, we don't know t final, and we don't need to know t final. So we'll use our y kinematic equation that doesn't have t final in it, and that would be Vy final squared minus Vy initial squared is equal to 2 Ay times y final minus y initial. And now we have completely modeled the situation. And all we have to do now is make it specific to this situation. Vy final is 0. Vy initial was 19.1. Ay is negative 9.8. And y final is what we want to know, and y initial is 0. So we have an equation, and the only unknown in it is y final. We can solve for y final, divide both sides by 2 times 9.8. We have negative 19.1 squared over 2 times negative 9.80 is equal to y final. And that is Negative 19.1 squared divided by 2 times negative 9.8. And that is y final is equal to 18.6. And we know that we're dealing with our basic metric units for y, which would be meters. 18.6 meters is y final, and that is how high the ball rises. So once again, we answer these questions by completely analyzing the situation. We have to get all the information we can out of the question statement. Some things are given explicitly, and some things we have to infer. We had to infer Vy final from the fact that the ball was at its highest point, which means that it's not moving up or down at that time. And we also had to infer the acceleration from the fact that the ball was up in the air and we were in a projectile situation. Now, let's think about the second half of that question. And the question was, how much time will elapse from the time that the ball leaves the bat until it reaches the fielder, who is back on the ground? And at what distance from the home plate will the fielder be when he catches the ball? So I would like you to draw that diagram. List all the knowns and unknowns that you can for that situation. And remember that the initial situation is going to be exactly the same. Just now, instead of stopping our clock at the top of the parabola, it's going to come back down to the ground. So you're going to have the full parabola. And think about what you know for the final situation. Think about what kinematic equation you might use, and try and answer those questions. Okay, let's draw our diagram for that situation. I have x and y. The ball starts from here. Now it goes up in the air and it comes back down to the ground. Draw it in its parabola. And just as last time, we have t initial equals 0. We can start that. Start our stopwatch wherever we want. We have x initial is equal to 0. Y initial is equal to 0. And our initial velocity is exactly what we calculated before. So Vx initial is equal to 11.0 and Vy initial is equal to 19.1. We know that the acceleration, ax, is equal to 0. Ay is minus 9.80 because we're in free fall. Finally, we have t final, which we don't know, x final, which we don't know, y final, which we do know. We know that the ball came back down to the same height, so we know that y final is 0. Vx final, which we don't know, and Vy final, which we don't know. Well, let's answer the first question. What is t final? T final we can find from our y kinematic equation. So once again, this is a kinematic situation. And we'll start with y. And why do we start with y? Well, we know everything about y except Vy final and t final. So if we ignore Vy final, then we can find an equation relating y final to t final. So we want our y equation that doesn't have Vy final in it, and that would be y final minus y initial is equal to Vy initial times t final minus t initial plus 1/2 ay times t final minus t initial squared. Okay, what do we have here? Y final is 0. Y initial is also 0. Vy initial is 19.1. T final, we don't know, minus 0 plus 1/2 ay, which we know is negative 9.80, times t final minus t initial, which is 0, squared. And you can see that we have an equation here that only has one unknown in it, t final. Let's simplify it a little bit. 0 equals 19.1 t final plus 1/2 of negative 9.80 times t final squared. What can we do from that? Well, let us add 1/2 times 9.80 times t final squared to both sides, and that would be 1/2 of 9.8 t final squared equals 19.1 t final. We can divide both sides by t final, and that would have, well, let me go ahead and draw that in, t final. T final divided by t final is 1. We don't need to write that. T final squared divided by t final is just t final. And so we're getting pretty close to our answer. I'll multiply both sides by 2, divide both sides by 9.8, and I'll have t final is equal to 19.1 times 2 divided by 9.8, which means that we can answer the question. T final is equal to 19.1 times 2 divided by 9.8. And that gives us 3.90, and our basic metric unit of time is seconds. So we know that the ball, for its entire arc, takes 3.90 seconds. So that was the first question we were asked. How much time elapses while the ball is in the air? The answer, 3.90 seconds. Now that we know t final, we can go back to answer the other question that was asked. What is x final? So now we know that t final is 3.90 seconds, and we want to know x final now. Well, once again, we don't know Vx final, so we could use a kinematic equation for x that doesn't have Vx final in it, and that would simply be the same equation that we used for y with x in it. So our x kinematic equation would be x final minus x initial equals Vx initial times T final minus T initial plus 1/2 Ax times T final minus T initial squared. X final is what we're looking for. X initial is 0. Vx initial is 11 meters per second. T final, we now know, is 3.90 seconds minus T initial, which is 0, plus 1/2 Ax, which is 0, times T final, 3.90, minus T initial, which is 0, squared, or X final is equal to 11.0 times 3.90, because this final term here is 0. It has a 0 for acceleration in it. So X final is 11 times 3.9, or 42.9 meters, since we're dealing with distance. So now we've answered the second question that we were asked, is how far away is the fielder from home plate when he catches the ball? The answer is 42.9 meters. So when the ball was hit, it went up in the air. We know that it went to a height of 18.6 meters. It took a total time up in the air of 3.9 seconds. And when it finally came back to the ground, it was 42.9 meters away from home plate. So that was a lot of work, wasn't it? And it seems awfully complicated, and I know that. The important thing here is that you follow the process. You draw your diagram, you list your knowns and unknowns, you infer whatever you can from the statement of the exercise, you identify the proper starting equations, and you follow through with your math. That's all very complicated, and it's a skill that you're learning. It takes practice, it takes exercise, and that's why we practice. That's why I give you extra assignments to work on at home so that you can develop this skill, so you can practice this skill. It's a very important skill. You can apply it in a lot of situations. It develops your analytical skills, it develops your math skills. It's the reason why you're taking this course. And the only way to develop these physics skills is to practice them. So practice your homework, practice, practice, practice. If you do the assigned problems and you find that you need more practice, well, there are plenty more exercises in your book. You can work on exercises until you develop the skills, until you're confident in your physics skills. That's what we're working on. That's why we're taking this class, so that you can develop physics skills. Next time, we'll talk about what happens when we can't ignore air resistance. Up to now, we've been ignoring air resistance, but I would like to teach you what happens when we can't ignore air resistance, and we'll pick that up next time. Until then, practice your skills and think physics.